Namaskar friends, myself Dr. Ashwini Kumar Gupta. Today I will start with lecture 10 of the series of General Organic Chemistry. As you remember in last lecture 9, we have done tautomerism, then hydrogen bonding, intermolecular hydrogen bonding, intramolecular hydrogen bonding, then stereoisomerism, in which we saw different types of stereoisomerism like configurational isomerism, conformational isomerism, then you can cis trans isomerism, that is geometrical isomerism. Okay? And obviously there are different types of, as I told, tautomerisms like ketoenol tautomerisms. Okay? So today I will start with the lecture 10, in which we will see another very new topic of chirality. Means it is a continuation of the previous lecture. So continuation of previous lecture, same thing. It is some related to stereoisomerism only. Okay? So we'll start the lecture. By asymmetric carbon atom. Symmetric carbon atom. As in the previous lectures, we have seen there is primary carbon atom, secondary carbon atom, tertiary carbon atom, then alpha carbon atom, beta carbon atom. Okay? So this is one more type of carbon atom which is known as asymmetric carbon atom. What does this happen in asymmetric carbon atom? In asymmetric, as we know, carbon has a 4 valency. That means it will be attached to 4 groups or atoms. Okay? And if to carbon atom 4 different functional groups are attached, 4 different functional groups. Take for instance CH3, Cl, then say OH, and take simple H. So if C, Cl, OH and H, right? Then 4 different atoms, you can say, they are attached, 4 different atoms. So such type of carbon atoms are known as asymmetric carbon atom, which are marked by asterisk. If a carbon atom is an asterisk, that means it's a asymmetric carbon atom, right? Now, so we will see a non-superimposable mirror image. Imposable mirror image. Mirror image of a asymmetric carbon atom. Carbon atom. You can say it is known as chirality. Non-superimposable mirror image. If you remember the previous lecture, we have seen a non-superimposable mirror images of any compound is known as enantiomer. Non-superimposable mirror image is known as enantiomer. That means can I say enantiomers they show chirality. They show chirality, right? But if that means if they are superimposable mirror image, they are achiral compound. That means they do not show chirality, right? Now, take for instance, I will take for this example. Yes, the OH and then this is Cl. If we see the mirror image of it, this will be Cl, C, CH3, this will be OH and this will be H. So, right, this is A, take for instance, this is B. So, if we pick this whole molecule and keep it, try to impose on it, then they can't be imposable because Cl here and here it is H. So, I can say this is a non-superimposable mirror image. That means, can I say these are enantiomers? As in the previous lecture, I have to explain to you what do you mean by enantiomers. The non-superimposable mirror image of an asymmetric carbon atom is known as chirality. Right? Now, there are 3 different types of means by the 3 different types by which we can represent a 3D molecule. Means a 3D, how does a molecule look in 3D shape? Three different types of representation are there, right? First is line wedge representation. Flying wedge representation. Prior to that, what you should come to know what you mean by wedge. In wedge there are two types. One is known as solid wedge, right? And other one is broken wedge. What do you mean by solid wedge? Solid wedge means they are nothing else but bonds, which are indicated by these are solid. Fine. And broken means they are in a dotted form. Fine. So they are in a dotted form. This is solid ion. So, and another type of bond is a solid line bond. Solid line. That means it is the bond in the plane of paper. It is bond in plane of paper. What do you mean by solid wedge bond? Solid wedge bond, basically we can say it looks solid wedge bond. This indicates that the covalent bond is towards the observer. Observer means towards yourself, towards the observer, towards yourself. And dotted bond in the sense away from the observer. Away from the observer. Away from the observer. Take for instance, I'll give you an example. Take for example, this is C, right? Take for example, this is H, which is in the plane of paper. I will say, take for example, if I say like that, this is CH3. Take for example, this is OH, and another you can say Cl. So this is towards the observer, and this is away. In the 3D format, in 3D format we will see the CH3 is coming towards you, towards the person who is observing it. The CH3 means above the plane of paper, and dotted bond or broken wedge bond or dotted bond, whatever we can say, going away from the plane of paper, right? Okay, now we will see another type. Take for example, that was the first type of representation. Now the second type of representation is known as Fisher projection representation, formula representation. Fisher projection. Fisher projection. Now, what do you mean by Fisher projection? In this solid lines are drawn in a horizontal way. Solid line means horizontal bonds, and the horizontal bonds, and they are towards the observer. Horizontal bond, but towards the observer. Towards the observer. Solid bonds are horizontal bonds and towards the observer. And Similarly, vertical bonds. Bonds, they are away from the observer, or below, away or below the plane of paper. You can say plane of paper. Towards the observer, above the plane of paper. Fine. Now, example I will tell you. Take for example this. This is CHO. This is OH. This is H, and this is CH2OH. Now, the longest carbon chain in a molecule will be always in a vertical format. This is the vertical format, vertical bond. That means it is always away, means it's going below the plane of paper. So this is vertical bond. This is vertical bond. And this happens to be right, and this happens to be the horizontal bond, right, and vertical. And these vertical bonds, they are attached to such type of functional group which can be easily oxidized. Vertical bond with highly oxidized functional group. Oxidized functional group. Oxidized means you can easily oxidize it. Means you can easily attach carbon. You can add carbon. Oxidation, as we know, oxidation we have seen in class 9, class 10. Oxidation means addition of oxygen. Addition of oxygen. Right? Or you can say removal of hydrogen. Addition of oxygen or removal of hydrogen. So in vertical bonds, which goes away from the bond of paper, away from the plane of paper, those here they are attached to two functional groups which can be easily oxidized. Not this, not this. These are coming towards the observer. These are coming towards, and these are going away. Right? Now, the third type of projection is nothing else but called as Sawhorse projection. Sawhorse projection formula, right? First one we saw, the second one Fisher projection. Now it is Sawhorse projection formula. This is very important. Huh? Just make a note of everything. If it is vertical, that means it is going below the plane of paper and with highly oxidized functional group. Whereas in the horizontal format means it is coming towards the observer. Right? Now it comes Sawhorse. Sawhorse formula is nothing else but it is a spatial arrangement of atoms. Spatial arrangement of atoms on two adjacent carbon atoms. Adjacent carbon atoms are indicated in a diagonal line, usually from lower left to upper right. For example, I'll show you. See, this is the diagonal and this is, sorry, fine. Now we will say this is A, this is B, and this is C. Similarly, this will be this will be, you can say this will be B. Take for example, this is C and this is A. Here it will be approximately, here it will be 120 degree. Again similarly here it will be 120 degree. And here also it will be 120 degree. Now this bond is equal to this bond. The second one is equal to this, and the first one is this. Now, so this is the first carbon atom and this is the second carbon atom, right? Now, you will see the left bottom carbon atom indicate that carbon atom is nearer to the observer. Left bottom, you can see bottom left. Bottom left, it is towards the observer. Left bottom, that means this. Left bottom is this. Left bottom is towards the observer. And right upper, that means this. Right upper carbon atom, right upper carbon atom is away from the observer. Away from the observer. Right? Away from the observer. Yeah. Now, this is known as staggered conformation. Staggered conformation. In this, the bond angle of 1A. This is 1. It's the second. 1A. That means this. 1A and 2A. That means this. 1A and 2A is 180 degree. 180 degree. Similarly, 1B is equal to 2B, which is equal to 180 degree. 1B and 2B. 2B. 1B and 2B. Right? Is equal to 180 degree. Similarly, 1C and 2C. 1C and 2C. Here also 180 degrees to each other. Try to understand this. 1A and 2A. 1A and 2A, they are at a 180 degree angle. Similarly, 1B and 2B. 1B and 2B, they are at 180 degree. Then 1C and 2C, they are at 180 degree. Similarly, 1A is parallel 1A, this 1A is parallel to 2A. It's parallel to 2A. 1A and 2A are parallel to each other. Similarly, 1B is, this is a notation of parallel to 2B. Fine. And similarly, 1C is parallel to 2C. 1A is parallel to 2A, 1B is parallel to 2B, and 1C is parallel to 2C. Right? So this is about the staggered conformation. Right? Now, the other type of conformation in this sawhorse is eclipsed conformation. Eclipsed conformation. Now, what do you mean by eclipsed conformation? It is the same thing. It is diagonal. Here the bonds are a bit, you can say, like that. This is A, this is B, this is C, you can say. Similarly, this is A, this is B, and this is C. This is carbon atom 1 and this is carbon atom 2. Now, you can see 1A and 2A, they both are in line with each other. That means, can I say the bond angle between 1A and 2A is 0? That means 1A is eclipsed. Sorry, 1A is equal to same as 2A, which is 0 degree Celsius. Sorry, extremely sorry. It is 0 degree. Similarly, 1B is equal to 2B, which is equal to 0. Similarly, 1C, 2C, which is equal to 0. So from this, can I say you can say the 6 bonds they lie on one upon other. If I see from the carbon atom, if I see from the carbon atom, take for instance, if I look from here, this is my eyes, when I look from here, then this bond will be exactly over this. This bond will be exactly over this, and this bond will be exactly over this. Right? So this is known as eclipsed. Similarly, you can say, that means I can say 1A is again parallel to 2A. Sorry, just now we saw fissure, then we saw sawhorse. In sawhorse we saw eclipsed and staggered conformation. So another and the last one is Newman projection. Newman projection. Newman projection. Right? Now, what do you mean by Newman projection? It is somewhat similar to our sawhorse projection. Somewhat similar to sawhorse projection. If again in Newman, when it is viewed along the axis, in all the 3 cases it is viewed along the axis only. Now, in Newman projection, if it is viewed along the axis, take for example the carbon atom which is towards the observer, right? That is front carbon atom. Now I'll go to the next page. I'll just delete all these things. Newman projection. Suppose, as we saw in staggered, like that it was, right? Like that, like that, like that, and then we saw, sorry, we saw like that. Right? This was like a sawhorse projection. The same thing, if you just straight, here it is diagonal. Now you see in a straight fashion. You observe the molecule straight, right? It is in parallel with your eyes, what you are observing. So suppose now this is the frontal one and this is the back side one. The frontal carbon atom, that means it is which is towards myself, front. That carbon atom is shown by a dot. This I will show you. This is a round carbon atom and this is a big dot. You can say the carbon atom which is, take for instance, this is the one carbon atom, this is the second carbon atom. I will say this first carbon atom, it is towards me, it is in the frontal position, it is towards the observer. Then this is 1, which is shown in like a dot. And 3 bonds are there, like that, and then like that. I will see 3 bonds. Fine. It will be, one will be A, the other will be B, and the other will be C. Right? Now, the carbon atom which is on the other side, which is away from the observer, is this. This is away from the observer, and this is towards the observer. Away from the observer, towards the observer. It's away, then it is shown like a big circle, and if it is towards, then it is shown like a small point. Then it is shown in 3 bonds like that. And now in this case, the bonds will be there. So this is the 1 bond, this will be the 2nd bond, and this will be the 3rd bond. Right? This will be 1 bond, this will be 2nd bond, and this will be, take for example, I will say this is A, this has B, and this has C. Right? So on this circle, the circumference of this circle, here 3 lines are drawn, 3 bonds are drawn. That means indicates it is on the far side, on the away from the observer carbon atom. The towards the observer carbon atom is denoted by a dot, but the away from the observer, it is denoted by a round circle, and 3 here. Right? Now suppose, imagine if I rotate it. If I rotate one of the carbon atom, keeping the other carbon atom stand still in a fixed position, the other carbon atom is rotated slowly. So a one position, one point it will come. For example, this is A, this is B, and this is C. Now if I rotate this, then this becomes, B comes here, A comes here, and then C comes here. Fine? C comes here. That means, can I say the carbon atom which is away from the observer, when I rotate it in the anti-clockwise, then these bonds are coming. So one instance it will come when this bond and the bond which is attached on the frontal carbon atom, can I say they can be behind each other? Just imagine carbon atom in the front and the carbon atom in the back. The frontal one is kept fixed and the other one you rotate it. So when you rotate it, the first carbon atom and the second carbon atom can come in front to each other. They will overlap. All the 3 bonds will overlap with each other. The 3 of the frontal and 3 of the back side. The 3 bonds of the frontal and the 3 bonds of the back side, they will come and overlap on each other. Right? So such type of conformation is known as eclipsed. eclipsed. First one was staggered conformation, and this is eclipsed form. And eclipse formation is the conformation is same. The staggered one is rotated. The staggered one is rotated. Right? In the previous case of sawhorse, as we had seen, it is in a diagonal form. In a diagonal form. Imagine the same diagonal form when put in a type of a circle. Right? This is known as eclipse formation. That means, can I say here the bond angle will be 0? Here also the bond angle will be 0. And here also the bond angle has to be 0. Fine. So eclipse form conformation and staggered conformation, right? Now, we'll come to another different topic. Now, as we know, in ordinary light, what does ordinary light contain? They consist of electromagnetic waves. As we have learned in physics, electromagnetic waves. Ordinary light contains electromagnetic waves, and which has oscillations. And the oscillations of these electromagnetic waves, they are the oscillations of electric and magnetic field. That's why it is known as electric and magnetic field. They have the oscillations of electric and magnetic field in all possible planes. In all possible planes. Right? In all possible planes. That is, you can say perpendicular. This is the sign for perpendicular. Perpendicular to the direction of propagation of light. Propagation of light. See, these are a typical type of physics term, but you should be knowing. Because in physics, you know all these things. Electromagnetic waves, electric and magnetic field, then field in the possible plane of possible planes. Just take, for example, I will tell you in a very simpler fashion. Suppose this is a light, cross sectional of the light. Here the planes will be in all possible direction, like that, like that. Fine, in all possible direction, right? This is nothing else but an ordinary light. Now, there is something called, you might have read, as nickel prism. Nickel prism is like a prism. It is made up of nickel. Okay? Nickel prism. Now, what do you mean by exactly by this nickel prism? What does this nickel prism do? Nickel prism, whatever. Now, this ordinary light which is there, in which the planes are in all possible directions, and when this ordinary light passes through a nickel prism, take for instance, if there is a nickel prism, take for example, this is the nickel prism, right? When there is a nickel prism, then what will happen? It will pass through it, and here the light which will come out will be only in single plane. The ordinary light will have only single plane, means only one possible direction, right? Here it was in all possible planes, but here it will be only and only one direction, one plane only, towards the one plane, towards the direction of propagation of light, only one single plane. So such type of light is known as plane polarized light. What do you mean by plane polarized light? Plane polarized light, first thing, when ordinary light in which the plane, in which the fields are in all possible planes, that is perpendicular to the propagation of light, Similarly, when they are passed through a Nicol prism, the Nicol prism, what it does, it changes the plane of all possible planes into a single plane, to a single plane. Okay? In only one single plane. The light oscillates in one single plane. So such type of light is known as plane polarized light. Henceforth, I will call it as PPL, plane polarized light. Right? Just a second. Right? Plane polarized light. Now, when the light comes out from here, right? When take for example, this is a sample tube which contains a asymmetric carbon atom compound. That means a compound which contains asymmetric carbon atom. Asymmetric carbon atom means to a carbon atom 4 different functional groups are attached. Right? Now, when this plane polarized light passes through this, okay, now after this the light comes out, then there is an analyzer. We'll study in detail. What do you mean by analyzer? Means when it passes through the asymmetric carbon atom, the analysis happens. The analysis we will do it in the next topic. Just now we will do it. First of all, you try to understand this diagram. All possible direction, Nicol prism, one single plane known as plane polarized light. Then it is passed through an asymmetric carbon atom, not any normal carbon atom. Such a carbon atom which should have all the 4 different carbon atoms. So that means asymmetric carbon atom, all 4 different carbon atoms. Then that light passes through an analyzer. Now what is this exactly? What is this analyzer? I will tell you just now. Fine. Make a note of it. No. But what happens? The compound that rotates the plane polarized light, as I had told you in the just now, I have told you that analyzer is there. Just imagine analyzer is like a voltameter. Just try to imagine voltameter. As we say in voltameter, it is a round in which a needle is there. Okay, for example, this is a needle. Now, whenever a plane polarized light via a symmetric carbon atom passes, and when it comes and falls on this analyzer, then what happens? The analyzer will either go this direction or in this direction it goes. Means either clockwise or anti-clockwise. This analyzer, the direction of this light, the direction, either this it will go in clockwise or in anti-clockwise fashion. Now, the compound that rotates the plane polarized light, that means the plane polarized light has been rotated, therefore this needle is going either in the right direction or in the left direction. Such type of property is known as optical activity. Optical activity. So what do you mean by optical activity? Optical activity means compounds which rotate the plane polarized light. Compounds which rotate the plane polarized light are said to have optical activity, and the compounds are known as optical isomers. Optical isomers, and the phenomenon is known as optical isomerism. Right? Optical isomerism, compound which rotates the plane polarized light is the property is known as optical activity, and optical activity gives rise to optical isomer. And this whole phenomenon is known as optical isomerism. Right? Now, if the voltameter rotates, if the plane polarized light rotates towards the right, that means clockwise. if the plane polarized light rotates this analyzer towards the right hand side, then it is known as dextrorotatory. The compound is dextrorotatory. Dextrorotatory. If the compound rotates the plane polarized light in the right direction, on the right, that is on the clockwise, right? That means clockwise. Then it is known as dextrorotatory, which is indicated by D, or also plus with a positive sign. D or plus. If something D plus something name of the compound, then that means D, small d, not capital D. Small d is known as dextrorotatory. Either you can also write plus. Similarly, if the pupil rotates towards the left or anti-clockwise, then it is known as levorotatory. L-A-V-E-O, levorotatory. Levorotatory, or you can say small l or minus. Levorotatory, L or small l, right? Levorotatory. And now, this is nothing else but purely an experimental phenomenon. Experimental phenomenon means by experimentally only we will come to know whether the compound phenomenon. This is experimental phenomenon. That means only experimentally we can find out whether the compound is a D isomer or an L isomer. D isomer or a L isomer. That means depending upon the rotation of the plane polarized light, right? Now, for example, I will take one example. Take for example, this is CH3. Now this is H. I will say this is Cl, and this is, you can say, CH2, CH3. That means ethyl. The name of this is 2-chlorobutane. This is also known as plus 2-chlorobutane. Now, how this plus has come? Only by experimental. For us, it is the asymmetric carbon atom. Then it will rotate the plane polarized light. Now, in this case, this 2-chlorobutane is rotating the plane polarized light in the clockwise direction. Therefore, it is plus. Similarly, suppose if I take the mirror image of it, it will show same way. H, CH3, then CH2, CH3, then Cl. This is nothing else but minus 2-chlorobutane. Right? 2-chlorobutane. Right? This again, I'll say this is an experimental formula. Not by virtually seeing the structure of a compound, we can say at this juncture, I'll say, at this point, whether it is a dextrorotatory or a levorotatory. Right? Now, asymmetric carbon atom nomenclature. Now, as in the previous case, we had seen that dextro and levo, it was only with respect to experimental form. Now here we have to give the nomenclature of asymmetric carbon. Right? What is the how can we write the nomenclature? Now step 1. Now here the chiral carbon atom, that means there are 4 different functional groups. So if you give the priority to this functional group, if these functional groups have to be given the priority by which functional group should come first and which functional group should come second. right? That means you should be in the 1, 2, 3, 4. In the highest functional group, which functional group has to be given the first priority and which has to be given the second priority. So what is the criteria for judging it? Is atomic number. Atomic number of a particular functional group decides the priority. Priority of a functional group. That means a priority of a functional group depends upon its atomic number. Now, atomic number is such a value you can find out easily. You know what is the atomic number of XYZ term, so we can say, right? Now, the atomic number of the highest priority group, highest priority, depends on the highest atomic number. Highest atomic number. Highest the atomic number, highest is the priority. Highest the atomic number, highest is the priority. And accordingly, we will see all the atomic number of individual functional group. So highest is 1, then the next one is the lowest is the second, and then third lowest is this, and the fourth lowest is the fourth functional group. That means I can say the lowest atomic number is of the lowest priority. Highest priority atomic number, that means this will be 1 and this will be 4, the priority number. We will take an example. Suppose this is COH and this is OH. This is Br and this is H2. Right? Now as per the priority, if we see, now this is directly bonded to carbon atom. This is directly bonded to carbon atom, but this is directly bonded to Br, which has the highest atomic number. So this will be given the first preference, right? And then this carbon atom is directly bonded to oxygen, and this is bonded to just carbon, and this is just nitrogen. Among the nitrogen and oxygen is the highest atomic number, so this will come second, and then comes 3, and then comes 4. That means the atom which is directly attached, to the functional group, attached the atom of a functional group, when it is attached to the asymmetric carbon atom, the atomic number of that particular atom has to be considered. Now, see this 1, 2, 3. That means it is 1, 2, and 3. That means I can say it is in this format. That means it is clockwise. That means it is R. Similarly, C, if it is F, this is H. Right. So this will be 1, this will be 2, this will be 3, and this will be 4. So it will be 1, it is like that, 1, 2, 3. So this will be S. This will be R. Configuration is on the right hand side, right? It is going on the right hand side, so it is R. The German, actually R has come from the term rectus, which is a German word, rectus. In German word, rectus means R on the right hand side. That means on the clockwise. Clockwise is denoted by R, and anti-clockwise is known as S. S is sinister. Sinister means on the left hand side. Sinister, that means on the left hand side, right? So you have understood what you mean by R configuration and what do you mean by S configuration. R means atomic number. If it is in a clockwise direction, then it is R, and if the atomic number priority is in the anti-clockwise direction, so it is S, right? So this is R and S type of nomenclature of a particular asymmetric carbon atom. Now we will do one more example, which will be slightly more complicated, but it's very useful. Take for example, this is carbon atom. On this I is it's situated. This is CH2 Br, and this is CH2 CH3. Then this happens to be CH2 I. Fine. Now since I is directly directly attached to carbon atom, so this will get the first preference. Now here there is a confusion, because here also carbon atom, here also carbon atom, here also carbon atom. When such a scenario arises, when a same type of atoms are attached, then how to differentiate? You have to go to the immediate next atom. Suppose here this carbon atom, all the three carbon atoms are same, but here the another atom is hydrogen. Here also another hydrogen, here also another hydrogen. Again here two hydrogens. Again there is no, you are not able to decide who will be given the first, second and the third preference. Then if this also is not unable to decide, then we will go here. Here is another CH2, here also is another CH2, but here also is another CH2. Even this is also same, matlab this is also same, this is also same, and this is also same, right? But here now, here this carbon atom is attached to I, right? And this is attached to Br, CH2 Br, CH2 Br. That means here it is CH2 Br and CH2 I. Now as per molecular formula, as per atomic number, this will come second, this will come third, and then this will come fourth, right? Because I has a highest atomic number as compared to bromine. Because if you know, it's F, Cl, Br and I, right? 9, then 18, right? Like that. So I, so this will be the second. Now it is going like that, 1, 2, and in this format. So it is an S isomer or S configuration. I hope you have understood this. If now here 2 CH2s, here also 2 CH2s, here also CH2s. If like that the case happens, then the immediate next carbon atom is considered Br, CH3. So this is one of the type which you will be getting it. Now what happens? The functional groups which are attached to this carbon atom many a times may not be a single bond. It can even be a double bond also. So if a double bond or a triple bond is added, functional group is present. That means a double or triple bond is linked to a symmetric carbon atom, or chiral carbon atom. Then that atom is duplicated. Then that atom is duplicated or triplicated. I'll show you what do you mean. Duplicate means the Xerox copy, and triplicate means two copies, and here triplicate means 3 copies. I'll give you an example. Take for instance, you have C double bond O. Fine. Now how does this C double bond O you will consider in RNS compound? Here C is attached to one oxygen and the other attached to another oxygen. Like that you will have to indicate. When you will get confused between this is same, and now C double bond O also will come. Now in this case scenario, this is not just C double bond O, but this is C single bond. That means two C single bonds and O. That means these are duplicated, right? Duplicated. Similarly, if C triple bond N is there, so this will be C bonded to 3 bonds because 3. So indirectly for this carbon 3 N's are attached. 3 N are attached. So depending upon the number of double bonds and triple bonds, here double bond is there, so 2. Here triple bond is there, so 3, and all the 3 position nitrogen. Suppose, right? Take for instance carboxylic acid, C double bond OOH. Fine. Now it will be C like that, then like that, right? C, it will be like that, and obviously this will be the OH, whatever, right? CO like that. So always if double bond and triple bond are attached to a chiral carbon atom, then the double bond is duplicated and the triple bond is triplicated. Like in case of CN, that is cyanide and cyanide, and in case of C double bond C double bond O, that means acetone, that means ketone. This is a carboxylic acid. Fine. We'll take one example in this case now. Take for instance C is attached to OH. One more example we will see. Now, okay, so these 2 types we have seen. We will see another type. Now what will happen? See, suppose OH is attached. Take for instance CH3 is attached. This is solid wedge bond, means towards the observer, that means CH2OH you see, and this is, take for instance H. Now here lies the catch. See, 1 I will tell this as 2, this as 3, and this as 4. So now if for first instance if we see 1, 2, 3, that means clockwise, that means my perception it should be R configuration, yeah, R isomer, but it will be only and only if the lowest priority group, suppose, is away from me. Lowest priority group should always be away from the observer, should be away from the observer. If it is away from the observer, the lowest priority, here H is the away from the observer, then it will be properly, then it is proper R. Now if I take another example, take for example, you can say take C, take C. If for C one ethyl group is attached, take for example ethyl, then CH3 is attached, then you can say H is attached, and here you can say another OH is attached. So now this is O, so this will be 1, right? Now this is CH2, right? Because here it is CH2 CH3, but the C is bonded to 1 C is bonded to 2H, and then again C. Here C is bonded to 3 hydrogen, then this has to be given the first preference, as from the previous scenario I have told you. This will be the third and this will be the fourth atomic number wise. But there is a difference. Here the fourth isomer has to be always away from the observer, but in this case it is towards the observer. So if I say like that again, 1, 2, 3, at first instance it will look like it is R configuration, right? Here it is R configuration only because the lowest priority group is away from the observer, but in this case the lowest priority group is here it should be lowest priority is away from the, but here it is lowest priority is towards the observer. If it is towards the observer, then it has formed R configuration, right? Now it is, since it is towards the observer, then this automatically this will become, you have to write it S configuration. Just try to understand. If the lowest priority is away from the observer, then it is normal R configuration on the clockwise and the anti-clockwise. But if it is the lowest priority group is towards the observer, then whatsoever is the configuration, you have to take the opposite of it. The naming has to be done the opposite, right? If it is R, then it will become S. Then if suppose in exam it comes, then your answer should be S configuration. Don't write R configuration. R only and only if this is away from the observer. But so the first thing you have to see the lowest priority group where it is, whether it is towards me or it's away from me. If it is towards me, then I have to take the opposite. If it is away from me, then whatsoever is the natural, whatever is the configuration is coming. Just make a note. It is very, very important. People try to they forget it off. They straight away they see 1, 2, 3, then this is R. 1, 2, 3, then this is S. But you have to see whether the lowest configuration, lowest priority group is where it is away or it is towards me. If it is away from me, then it's proper. Then it is no issue. Then whatsoever is the configuration, that is. But if it is towards me, then whatever the configuration is coming, I have to take the opposite of it. I have to take opposite of it. So that is this, right? Now, as we saw R and S type of configuration, the another configuration is ENZ system of configuration. ENZ system of configuration, right? Of nomenclature basically. But this ENZ system of nomenclature, as in the previous case, R and S was mainly meant for asymmetric carbon atom. It was meant only for asymmetric carbon atom. But now this what happens? The ENZ system of nomenclature, it is meant for geometrical isomers. Geometrical isomers. That means the isomers which are formed due to the restricted rotation along the C double bond C. If you see the previous lecture, I have told you what do you mean by geometrical isomerism. Geometrical isomerism, the isomers formed due to the restricted rotation along the C double bond C. Right? In this scenario, it's not compulsory that all the 4 carbon atoms, take for example C double bond C, na? See, take for example, if I take so on this adjacent carbon atom, any 2 functional groups have to be same. That is the first condition. Any 2 functional group or atoms have to be same. On the adjacent carbon atom. Not on the same carbon atom, on the adjacent carbon atom. That means the neighboring carbon atoms, they have to be, that means you can say vinylic carbon atom. I have told you. What do you mean by vinylic? Vinylic means neighbors on these vinylic carbon atoms. So we'll take a simple. Take for example C double bond C. Suppose this I take as Br. This I take as I. This I take as, okay, let it be. I'll take F to be more a bit complicated types. F. Then this I will take as Cl, and this I will take as, can say again, I. Right? Right? Now, any 2 functional groups. Take for now, what is the with respect to atomic number? With respect to atomic number, this has to be 1. This has to be 2. This has to be 1. Sorry, fluorine. Atomic number of fluorine will be first. Sorry, chlorine will be first. Chlorine will be first and fluorine will be second. Right? Chlorine. Now, these two 1, 1 are the same. right? This two are the same. What I have told, two functional groups having the same atomic number, numerical value with respect to atomic number. Try to understand. With respect to atomic number, this is 2 here, this is 2 here, this is 1 here, this is 1 here, right? If the highest priority group across the double bond, if the highest priority group across the double bond are on the same side, highest priority group is on same side, highest priority group is 1, is the highest, 1 and here 1, these two numerical values are the same, right, with respect to the atomic number. They are on the same side, they are on the same side, then it will be known as Z configuration. Z configuration. Z, again this is a German one. Z means Zusammen it is something. Zusammen. Just don't go on the name. It's something it's very difficult for us Indians to pronounce it. This German language is German word. Zusammen. You just in short you say J configuration, Z configuration. If the highest priority group is on the same side, then it is known as Z configuration, right? Just make a note of it. E and Z system of nomenclature is with respect to geometrical isomers only. Geometry. Any two functional groups, the two functional group which are attached to the two adjacent carbon atom. If the numerical value of the functional groups are on the same side with respect to their atomic number, are on the same side. If so in that the highest priority group, which is on the same side, then it is known as Z configuration. Similarly, if the highest priority group is on the opposite sides, right, this is Z. Similarly, take another example, CC. Take for example, take I, then you take BR, take F, and then you take CL. ठीक है? Here chlorine is given the first preference, and here fluorine is given the second preference. Bromine is given the iodine is given the first preference, and bromine is given the second preference. Right? Now here the numerical value 1 and the same numerical value 1 is on the opposite sides. So it will be known as E configuration or E isomer. E is known as Entgegan. E-N-T, I think so, G-E-G-A-N, Entgegan. This is again the same thing, it is a German word, Entgegan, E configuration. So here the highest priority group is on the opposite side. In the previous case, the highest priority group was on the same side, right? The highest priority number, the numerical value, these both are same numerical value, 1, 1. They are on the opposite side, across the C double bond C, on the opposite sides, right? As we know, in case of cis and trans, the functional group itself should be same. That means if here there is I, then here also it has to be I, right? So if I are on the opposite sides, same. This here can be different, here can be different, but at least two functional groups on both the carbon atom have to be same at any cost. If they are on the same, or if they are on the opposite side, as I have told you in a previous lecture, it is trans isomer. If it is on the same side, then it is cis isomer. Now, that was with respect to having at least two same functions. But here, if all the four functional groups are different, then with respect to the atomic number, we have to go. Right? With respect to the atomic number. In that scenario, there was nothing like atomic number. There was just the nature of the functional group. Same functional group or dissimilar functional group. Fine? To E configuration. Now, there is something called racemic mixture. Racemic mixture. Now, what do you mean by racemic? So, we have finished these two types of configuration, R and S configuration and E and Z configuration. Right? Now, we will come to another topic by name racemic mixture, or even racemate it is known as. Racemate it is known as. Right? Now, what do you mean by racemate? Racemic mixture. When you get an equimolar quantity, finish this now. Equimolar quantity of D and L isomer or R and S isomer, right? DLN isomer or RNS isomer, the equivalent quantity. That means equimolar quantity. That means 50 of R and 50 of S. That means R will rotate on the right hand side clockwise and this will rotate on the left hand side. So I can see they both are cancelling each other. R and S, they both are getting cancelled. So it will be a RS mixture. This will be a DL mixture. This will be a DL mixture. This will be an RS mixture. Right? So obviously if the you can say equimolar 50-50 you are getting, means 50% of R isomer and 50% of S isomer. Right? 50% of R isomer, 50% of S isomer. Then obviously if that means it will not be showing any type of optical activity. That means no optical activity, I can say. Why? Activity. Even though it is rotating the plane polarized light, but the half portion is going on the left side and half portion is going on the right hand side. So on the half portion it is minus whatever value, mathematical. Take for example minus, if on the left hand side it is minus A, on the right hand side it is plus A. So minus A and plus A, they are cancelling each other to get a 0. That means it has no optical activity. That means a racemic mixture. A racemic mixture does not show optical activity. Does not show optical activity, right? A racemic mixture does not show optical activity. Fine. Take for example, same thing. As in the previous case, we had seen D2-chlorobutane. In the initial, I have told you what is D and L configuration. I have told you D means plus 2-chlorobutane. So, and similarly, if I say DL, L minus. So D, that was R and this was S. But suppose if this 2-chlorobutane, say. So if it is a 50-50 mixture, so optical activity is 0. Optical activity is 0. So racemic mixtures are what? The mixture which get equimolar quantity of either S isomer or equimolar quantity of RS mixture or DL isomer mixture is known as racemic mixture, racemic mixture or racemate, and they will not show any optical activity. That means they are optically inactive compounds. Why they are optically inactive? They are optically inactive. They are optically, even though they have a asymmetric carbon atom, which is of no point. That does not mean if you are having asymmetric carbon, and then you will have to show an optical activity. But if you get a mixture of isomer, asymmetric carbon atom. But if you get a mixture 50-50, then obviously it will be a optically inactive compound. That means one will be on left hand side, another will be on right hand side. I hope you might have understood now. This we come to an end of this stereochemistry part, stereoisomerism to be more precise. Stereoisomerism, in which I have taken all the basic things. You'll have to just go through this whole topic of the previous lecture and this lecture, and I think so. This is enough for today, and we have done a quite a big quantity of work we have done, and the video also has become quite lengthy. So just go through it and all the lectures, and try to compare this lecture with other lecture also. So by doing this, we have finished this stereochemistry, stereoisomerism part, right? So now I shall take a leave. So if you have liked the video, if you have liked this lecture, then please do say your friends or your known ones, so that they can also watch at this lecture. And as you know, today being today I think JEE mains has been out, and in JEE mains organic part is most important. Let it be irrespective whether it is JEE or JEE advanced or MST or BITS or Birla Institute, any or NEET medical, anything. Tell the name, and any engineering or medical exam organic chemistry is the basic, and the if your proper organic is the most easiest, but also it is more difficult. If you try to understand the concept, then it is easy. But if you don't understand the concept, then it is most difficult. So people try to score most in organic chemistry, and it forms the major chunk of the paper, right? So just give comments. If you are looking if you are watching this video at Facebook, then do follow my channel and write comments in it. And if you are watching the same video in YouTube, then do write the comments and like the video, and do subscribe my channel, right? Okay, so I'll meet you in next lecture with lecture 11, in that lecture we will see mostly now what do you mean by reaction intermediates, right? In which you have seen in class 9 and class 10. This that means you have seen cations, anions, right? You have seen cations, anions. Similarly, there will be carbocation by name is there, carbanion is there. Okay? So that will be taken into reactive intermediate. So now I shall take a leave, and I shall meet you in next lecture, right? Okay. Thanks.